Hello and welcome to my video, lesson 3, chapter 3, 4.2. So this is, again, based off of both chapters, and this is the second lesson in it, because we're talking about exponents and logarithms together. And so anyways, we're going to go ahead and start this. And so this is the parent function that is important to keep in mind, which has this description. That was from the last video. So you might want to go back and check that out. It's up here if you're unsure. But today we're really going to be focusing on this one, which is in the formula sheet. And we have these two ideas, which are new, but also the A and the B still. And so really, A is our initial amount, Y is like the final amount. B is the rate of growth or decay. T is the time, and then P is the amount of time it takes to increase or decrease once. So it's the compounding period, half-life period, doubling period, whatever else you might want to say. Okay. So we're going to be focusing on that version from the formula sheet. There are many different formulas that we can use. The simple ones that we are going to look at mostly are going to be finance, growth rate of organisms, and decay rate of radioactive material. But those are just some examples of what you could use these for. And they're all, a little bit different, a little bit interesting. The finances are probably the ones that's going to help the majority of people. With that said, if you go into ecology, then growth rate of organisms and biology and bacteria growth, that will all have to do with the growth rate of organisms, more important than finances. If you go into physics, which is my favorite, then the decay rate of radioactive materials might be more interesting. So, and there's more than just these three. These are just the three that I'm picking here, but keep in mind this stuff is useful for different reasons. Okay, so here we have a question. Consider a $5,000 investment into a PC money account with a 2.2% annual rate of return. This account pays for interest monthly and is therefore compounded monthly. Okay, so this 2.2% is an annual rate, but it compounds monthly. And we start with a $5,000 investment. How much money does the account have in it after 5 years? Okay, so if we're going to make an equation here, what we need to do is start with our initial amount of $5,000, and then we need to make it grow. And so to make it grow, we're going to go 1 plus, and then it's the interest rate. So it's the 0.02%. The thing is that interest rate is an annual rate of return. And so because it's compounding monthly, we actually want a 12th of that for every month. So every month we're getting a 12th of 2.2%. Oh, 2.2%. There you go. And then in the exponent position, it's going to be time, sometimes using n, sometimes using t, but time divided by 12. So for whatever reason, we just like to use time when we're talking about finances. We're using it very often in years. And so this is, 5 years, and then we're converting that to the 12 compounding periods per year because there's 12 months per year. Okay, so this is our initial formula, but the question asks us after 5 years, how much do we have? So this is going to be 5,000, 1 plus 0.022 over 12, and then 5 over 12. And so how much money are we going to have after that amount of time? So let's type this in our calculator. And notice that I'm typing it in exactly as written on the page. I don't want to accidentally have my brackets in the wrong place, so I'm writing it exactly with the fraction button. I press enter, and it's not very much extra money. Oh, you know why? Because we're not doing it right. This is backwards. This needs to be 5 times 12 because there are 5 years and there are 12 compounding periods per year. So this is actually completely backwards. And I could tell that it's backwards because our numbers are not big enough. Compounding interest is much better than that. Okay, so this is more reasonable. Now, this is a pretty terrible rate of return, but even still, it gets us to giving us an extra $580 per over that 5-year period. So it's actually not that bad. It's not great, but it's also much better than not having it in a savings account. So 5,580.82, I believe is what I read. 83. And then this is something I'm going to say by default, when we're talking about money, we're going to have it to the nearest hundredth, because nearest cent, because that's just what we do. Okay, so now we're going to consider, so that's a savings account, so that's nice, but it's 2.2%, which is not great. Consider the same $5,000 investment into a broad market ETF with a 10% annual rate of return. So this is a relatively standard rate of return that we can kind of expect to be reasonable. So it's a 5,000 and annual rate of return. The thing is that this account compounds annually because it's an annual rate of return. There's no extra money you're getting most of the time. There might be some dividends or something else that compounds more than that. So it could be a quarterly or something. But let's just go with compounds annually. Yeah, so we're going to write this down. We're going to go 5,000 times by 1 plus, and then this will be the 10% after 5 years. And you can see how much stronger that is. 8,052.55. Which, when you think about it, that seems kind of odd. Like, it seems like way more powerful than it should be. Because 10% is $500 times by 5 years. We should be at somewhere around, like if you're just thinking simple interest, if we got 10% of $5,000 per year, we should be getting that much extra, right? With a simple interest formula, we would expect at the end of the day to have $7,500 in the bank account. But with compound interest, we are able to grow at a much, much faster rate. And this is the beauty of compound interest. So our final answer is this 8,052 answer, which is over $500 more because it's compound interest. And it's just going to grow faster and faster the longer you can leave it in there. So again, should you have your money in a PC money account? No, it's better than just a regular bank account, which gives you like 0.2% or something silly, but it's still not great, right? Compared to a broad market ETF, it's not even close. Okay, let's keep going and just notice that we have a formula that we can use. So this is a formula if you want to memorize one. This is our compound interest formula. The thing to keep in mind, or the kind of extra note I want to say, is the n value. And it comes from the question. it comes from whatever wording it says. If it says compounds annually, that's once per year. So we have a 1 for N. If it says monthly, then it is 12 times per year. If it says weekly, then it's 52 times per year. If it says daily, then it's 365 times per year. But there's some other odd ones. There are semi-annually, which means 2 times per year. There is semi-monthly, which means 2 times per month, which means 24 times per year. There is bi-monthly, which means it happens every 2 months, so 6 times per year. There's bi-weekly, which means that it happens every 2 weeks, which is 26 times per year. And one more that I want to say, there is quarterly, which happens 4 times per year. So all of these words are words you should recognize. Some of them might be explained in the question, especially for a diploma question, but you should know these words. You should know what the word annually, monthly, weekly, and daily mean. Those ones should be obvious. And so all you got to do is you got to compare that. When it says semi, then you're going to multiply by 2. If it says bi, you're going to divide by 2. And then quarterly, it happens 4 times per year. So that one should be pretty straightforward as well. Okay, so we have this formula, we have these words. How can we go ahead and solve this next one? So you as an 18-year-old, I realize you might be a different age, but let's just pretend you're 18 for the purpose of this question. You can change this, by the way, to your age, just to see if you can find a more interesting answer. But anyways, you as an 18-year-old need to invest today in order to have $1 million by the time you're 65 years old. So how much do you need to invest today? Okay, so this is saying not a monthly addition every month, but just like how much money do you need to put in the bank right now, and then you just don't touch it. You don't touch it to take it out to get a mortgage. You don't touch it to take it out to pay for university. You don't touch it for any reason. You put it in the bank when you're 18 and you take it out when you're 65. Not just bank. You put it into a TFSA or RRSP savings account. Probably a TFSA, assuming, you're 18 because you won't have a pretty big income probably right now. So put it in a TFSA, and that means it's tax-free, TFSA, meaning it's a tax-free savings account. Put it in a TFSA today at 18 years old. How much will you have, or how much do you have to put in to get $1 million by the time you're 65? Now, what we're going to do is assume a few things, and some of these assumptions are maybe not perfect, but assume an annual rate of return of 7%. This is actually a pretty reasonable rate of return because it's the 10% increase that the broad market ETFs historically have gotten, minus about 3% for inflation. So this is a relatively fair estimate. It's not perfect, and like this says here, past success is not a perfect indicator of predictor of future success. So just because some ETF or market or whatever has done well in the past does not guarantee its future success. But that being said, this is what the market has generally done on average for the last 100 years. So it's probably a fair assumption, and you have to do something. So with that said, we're going to go ahead and try this out. So we want to have $1 million by the time we are 18 years old. So the question is, how much do I need to invest today, which is A naught, in order to get that? So I'm going to go 1 plus, and then I'm going to put in my interest rate. It'd be nice if it had a different compounding period, but we're just going to assume a 1-year compounding period. And then 1 times, we'll do 65 minus 18 up here. So all we're going to have to do is solve that in our calculator. I mean, putting a 1 on the bottom of a fraction is certainly not important. Doing a 1 times a number is certainly not important, but I'm going to plug it in exactly as listed. Okay, now this might seem like a crazy number because it is. It's not the amount you're going to be putting in. This is just a multiplier. Dot, dot, dot. Okay, and then we're going to divide $1 million by that amount in order to get our A naught. So how much do you need to invest today in order to have that amount at the end of the day? 587. So you need to invest 41,000 and 47. Okay, 41,587.47. So you may not have this money, and I don't blame you if you don't. I didn't have it at 18 years old. I barely have it now, just sitting around ready to be invested. I have savings, but you don't have this money just sitting around, and your parents aren't going to just lend you $41,000 right now. So there is another way of doing this. Compound interest is still quite amazing. There are plenty of calculators to show you how to save. So let's go ahead and look one up. I mean, that's pretty close. So if you invest $200 monthly for 47 years, then guess what? You're going to have almost $1 million. So there's lots of assumptions going on here, but the point I want to make is compound interest is actually way more amazing than people give it credit for. Okay, let's take a look at another question. Nuclear explosions, whether from purposeful war or testing results, resulted in harmful radioactive isotopes. So in 1963, there was a partial nuclear test ban, banning above-ground nuclear tests. People born before this date still have traces of an isotope called strontium-90, SR90 for short, given that it has a half-life of about 29 years, and that some people alive today still have measurable strontium-90 left in their bones, so 33 microbarcus or something. I don't know what that is. But this is it's a measurement of the amount of radioactivity that's happening, which is the way that they measure this. Anyways, how much did they have after the initial exposure? So how much did they start with in 1963? Okay, so if we were trying to solve this question, what we're going to do is just say the final amount is 33. What is our initial starting amount? I'm just going to call it A. And this is a half-life of 29 years. So this is going to be 2021 minus 1963 and then divided by 29 years because it's dividing by the half-life period. Now, what that's going to solve for is it's going to say it's a half-life, and I think it's going to have a 2 there. Is that what that ends up being? So 2021 minus 1963 over 29. Yes. I tried to make these numbers line up. I know it's not 2021 right now. For now, I'm trying to keep them having nice numbers, but honestly, it doesn't really matter, right? This could have a more modern number, and it would still be perfectly fine. Actually, why don't we do that? Why don't we change this to 2026, the year that we are talking about it. Okay, so if we do that, it's going to be 20. It's going to be 2 point something. So 2.17. All right, and if we want to find the initial amount, we just have to divide by that. So it's going to be 33 divided by a half-life of, and then I can make that 2026 minus 1963 over 29 to make sure it's a nice perfect result without any rounding errors, and I get 148.75. Let's just round up because I'm not sure, there's no rounding descriptions in this question. So let's just leave it there. All right, one more question we're going to do on this video, and then that'll be the end. An invasive species of plant, like the Canadian thistle, is introduced in a new environment. It is only noticed after it has spread a bit. So on the first year of the study, there are 46 plants per square kilometer. In year 3, a study finds 138 within a square kilometer. Assuming a exponential growth rate, how many plants on year 15? Okay, so there is a lot of information here, but not a lot of information at the same time. So 138 is the final amount. 46 is the initial amount. We do not know the growth rate. So I'll just put an R here for growth rate. But we do know that it was 2 years of that growth rate to switch to the 136. So what we can do is we can do 136 divided by 46, and then we can get the growth rate. This will be 3. And so this is it's tripled, but it's tripled per 2 years. So you could do this differently by square rooting the 3 and getting an answer for R, and then just having a 1 up top, or like every year it counts as 1. But you could also say, okay, well, it took 2 years to do that. Why don't we just make the period, the doubling or tripling period, 2 years? Okay, so the tripling period every 2 years. Okay, so with that in mind, we can go down to year 15 and try to figure out how many plants there are on year 15. So year 15 minus year 1, because that's where we started, means there are 14 years. And if we're tripling every 2 years, how does that look on our formula? Well, we want to know the final amount. And so it started with 46 times by the tripling rate. And then it's 14, but it's every 2 years. So it's divided by 2. That's the period, the t. So we can go ahead and plug this in. And we're going to get an answer. So this is times by, 14 over 2. And we get 100, that's maybe unrealistic, 100,602. That might be an unrealistic number, but that's what we have. All right, I hope that this video helps you better understand the concept of half-life and growth rate, decay rate, and especially the finances, which are very, very useful for real life. I hope this video helped, and good luck.